Okay, so factors affecting rate. The first of these factors would be the nature of the reactants. So the simpler the reaction, the faster the rate. And we're going to address this a little bit in a bit. Second, gases react faster fastest and solids react slowest. For kind of obvious reasons, right? It's the amount of energy and it's the amount of movement. Number 2, temperature. It increases the energy of the particles. To overcome the activation energy. So remember, the activation energy is in that. So this is the activation energy. And you have to get that much energy in order to actually make the reaction go. So that's a lot of activation energy, right? So raising the temperature or changing the temperature accordingly is going to help to overcome that activation energy. Now, there's a standard rule of thumb, which is like a weird saying I have to confront every year that I do these notes. Standard rule of thumb, which has to do something, by the way, with like the length of a person's thumb back during an industry, in a certain industry, there was a standard rule of the length of your thumb. Like this length of leather will cost you this much money. It's a standard rule of the thumb. That's where that came from. But I don't know what it was, but it was something like that. So standard rule of thumb is that increase of 10 degrees Celsius approximately doubles the rate. Now, this is a very interesting rule, and I'll explain why in a second. Because if you add energy to an exothermic reaction, you're pushing it back in the wrong direction. So in theory, it'll slow the rate down. Because exothermic means that energy is being exiting, and so if you add more energy in, then less energy will be exiting. It won't speed up the reaction, it actually will slow the energy down, the reaction down, because more energy is being added in instead of taken out. So it's like this weird concept, but this is a standard rule of thumb. So having that being said, you're going to have problems tonight that are going to say, we're going to raise the reaction 20 degrees, right? Which means we're going to double the reaction, and then we're going to double it again. Okay? And that also being said, your homework is on this, which is copied, which I'm going to upload. It's from another textbook because I've run out of problems in here. So, all right. Okay. The next one would be concentration. All right, so you can imagine increasing the concentration, if it's increasing the reactant concentration, is going to speed it up, because we've talked about double the concentration, rate changes by this. We've actually talked about that in class, right? So it increases the number of collisions. So if you increase the concentration, you increase the number of collisions that the particles have. And remember, the particles have to collide, and we're going to talk a little bit about this. The particles have to collide in order to react, and they have to collide in the right orientation. This is part of the collision theory, is that they can't just like bang together randomly. They actually have to bang together, but it has to be like in the right side with the right orientation. So if they bang together back to back, that's not going to worry. Head to stomach, that's not going to worry. Like, it has to be the right orientation, you know? Okay. So, surface area. Larger surface area increases. The number of spots for the collision. So how do you increase the surface area? You crush it, right? So I have a solid. What am I going to do? I'm going to crush it. This is why crushed ice melts faster than chunk ice. This is why you crush things in order to get the effect of them more. This is why if you're a hard candy eater, which I am, I chew the hard candy to get more flavor out of it, because it's got more surface area. And maybe in calculus, you've done the surface area to volume ratio. Did you do that? You didn't do that? All right, well, maybe we'll do that tomorrow. It's a whole thing. It's a whole nature thing that is a driving force through nature, the surface area to volume ratio, which we can take a look at tomorrow, because it drives both chemistry and biology in nature, surface area to volume ratio. And it's a whole calculus thing, it's a chemistry thing, it's a nature thing, it's an environmental science thing. So the larger the surface area, the more spots for collisions or reactions or feeding spots for an organism or chemical reaction spots for something in your body, the smaller it is to the volume of what it is. The more spots there are for whatever it is that has to happen on the surface can happen per volume. So also, when you stir, you rotate, right? The surface area, which increases the possibilities for collision. And then number 5, catalysts. Is a substance, and we've talked a lot about this, so that increases the rate of the reaction without being used up. And that's important, because we're going to talk about that hopefully today. Same thing with an enzyme. They're not used up. they go on to be used again. So enzymes and catalysts. All right, now enzymes in particular are reaction specific, and they create what's called an activation complex. And I'm sure, I know you learned about that in AP Bio, the activation complex. They're going to lower the activation energy by changing the orientation. So an example of this, okay, an example of this is you have a reaction that has to occur on the surface area. And so there is like these knobs on the surface area of a cell that has to occur. And what is going to happen is these things are floating by, like say these proteins are floating by, and they have to attach to these knobs, these nodules that are on the surface area. So there are these enzymes that link up with these nodules, and these enzymes grow up like trees. And what they do is these particles, they grow up like trees, and they wave these nodules around in the cytoplasm, the fluid, in the fluid. So they're waving them so that when these things fly, they're more likely to grab them, to react with them. And then once these things are pulled off, these enzymes here detach and float away and look for another spot to attach and do the same thing. That's an enzyme. It changed the orientation so that the reaction, it lowered the amount of energy that was needed for that reaction to occur by changing the orientation. It's very reaction specific because it's got a lock in here and it's got a lock in here, so it can only be used for that one reaction. That's an enzyme. Catalysts are things like heat, right? They're different. Catalysts are reaction general, and they can be used over and over again. Catalysts also change the pathway of the reaction. So for example, and so do enzymes, but catalysts, for example, a catalyst might be a manganese metal. And the manganese metal's job is to pull electrons off at a higher rate. And it does that in any reaction that it's in. So it will pull electrons off until the hydroxides get to a certain point, and then the hydroxides will start pulling off. So it makes it easier for the electrons to be transferred during a reaction. And any time that you add manganese into a chemical reaction, that's what it'll do. So that is a catalyst, because we want these electrons to be transferred, but if we add the manganese in, they'll be transferred faster. It will take less energy for that to happen, okay? So that we know, you could say as a scientist, well, what would happen if we added manganese in? Would that help? Because you know what the manganese will do. It's not reaction specific, okay? All right, next. Let's talk about the collision theory, because we've been talking about the collision theory a little bit. We've been saying like, oh, the collision's here, the collision's there, right? So first, to react, a molecule or an ion has to collide. So molecules and ions have to collide. Second, the collisions have to have proper orientation. And third, the colliding particles, and this is the part that gets into chemistry, particles have to have sufficient energy to break and form bonds. So that catalyst is going to be anything that can assist in one of these things. Can it help with orientation? That would more likely be an enzyme. Can it help to lower the amount of energy needed to break the bonds, or help to increase the amount of energy available to build the bonds? That's going to be a catalyst. All right? So again, we're going to see this again. Why? Because it's a highly likely graph. So here, the activation energy is here. Okay, this is the activation energy, and here is the catalyst. So notice, and these are the reactants, and these are the products, and this is the progress, and this is the energy. And this is on the test about once every other year. In some way, draw the line that will show the use of a catalyst, and all you have to do is show the line dotted with less energy needed. Okay, so same line, only this time we're going to show it as a products are here, reactants are here, activation energy is here, right? And so in this case, here's the catalyst. What did it do? It lowered the activation energy. Progress of the reaction and energy. Okay, so both cases, the catalyst, all it did was lower the activation, all right? So let's talk for a minute about the activation energy. It's the energy needed to start the reaction. And the collisions that we've been talking about, those collisions, they require enough energy to overcome, that's the phrase that's used, overcome the activation energy. And so therefore, because of that, the higher the activation energy, the slower the rate. Okay? Now, this leads us into reaction mechanisms. Now, reactions don't occur in one step. It's not like you pour things in and bam, it just happens. Reactions happen in multiple steps. And there are things that occur in between. They're catalysts that get added, and they're intermediates that are formed. So we're going to take a look at these, and then involves your homework tonight. Now, this can get very detailed, but what they include on the test is not very detailed. The reaction mechanism is a series of steps for the equation, going from reactants to products, right? So it's not indicated by the equation because it's steps. So you can't judge by the equation what the steps are going to be. You have to know experimentally. It produces intermediate products. So we need to talk about what those are. Intermediate products are produced in the reaction and then used up in the reaction. So in other words, if there are 3 steps to the reaction, you will see one of the products in step 1 is, for example, nitrogen monoxide. And then in step 3, nitrogen monoxide is a reactant. So it's produced in step 1 and then used in step 3 and gone. An intermediate. Showed up and then disappeared. It wasn't added as a reactant, it showed up as a product and then was used later as a reactant and disappeared. So we're going to take a look at that. There are slow steps. Slow and fast steps. There actually are like many different speeds. They rate them. But for us, there are only slow and fast steps. And the reaction rate equation must match the slow step. That's one of the things that you're going to see, is that when you finally make a decision about what your rate law is, it's got to match your slow step. So that means that the rate determining step is the slow step. So this is a little like driving long distance. So like I drive from here to Connecticut basically every vacation, every summer. I never stay here, right? And my entire trip is based on one thing: Washington, D.C. The entire length of my trip is based on Washington, D.C. If I get up there and it's bad, first of all, if the Senate and the Congress are in session, I have to judge my time of what time I get there. Because if they're not, there's nobody there. None of their aides are there. None of the Pentagon is, barely in session. Nobody's in session if they're not in session. Everybody takes their time off. But if they're in session, Washington's working. And then the Beltway, which is the road I take, it's 30 miles long. It literally can take me 2.5 hours to do that 30 miles because there could be an accident on it. Could be anything. I could be backed up. People could be pulled over literally with picnic baskets. It could be that bad. Okay. And it's probably maybe 42 miles. Or I can go through at 2 a.m. and zip through. And if I do that, it could be the difference between 17 hours and 20 hours drive. That would be the slow step. Your trip can only go as fast as your slow step goes, because I can drive 82 miles an hour all the way up and then hit Washington and blow my whole trip, right? And then I get on the other side of Washington and I'm great, sailing through, right? But that bottleneck can ruin my whole trip. So you got to think about the slow step like that. So you can have a fast, slow, fast, and it doesn't matter how fast your first two steps are going. When you hit that slow step, the pace of that reaction is only as fast as that slow step goes. So the rate determining step is that slow step. So reactions only move as fast as the slow step. And the rate law can be determined by the rate law of the slow step. Now, right away, you're thinking like, oh, wait, so that sounds pretty simple. And it is. And this is how AP kind of complicates things. Because instead of giving you just a simple equation, they give you 3 steps, and then they say, what is the rate law? And if they put an intermediate in there, then that intermediate would be gone, wouldn't it? Even though it's in the slow step, it would be canceled out. So you have to do the job to make sure that your slow step is pure and not polluted by an intermediate or a catalyst that's going to disappear. All right? And so that's what the problem's about. So we're going to take a look at a couple of these. So your acceptable mechanism all right, would add up to your net reaction, and we know this from Hess's law, right? They have to cancel out and add up. You know what I'm talking about, right? You stack them all up, you cancel out reactants and products and everything, and your bottom line should be the original reaction, okay? And then, in the end, your rate law should be from your slow step. So let's take a couple examples, all right? Okay. Alrighty. All right, so here's the first reaction. I think my dot can is dirty. Okay, so here's my overall reaction. All right. And here's my step 1. And notice there's a K1 and a K2 because each step has a different rate constant. Right? And there's a slow step and a fast step. terrible. I'm sorry, that's just terrible. All right, so there's two different Ks. Now, one thing that you want to pay attention to here is there is an intermediate here. Okay? Here's the intermediate. The intermediate came out as a product in the first step and then was used up as a reactant in the fast step. So that defines it as an intermediate. It isn't a reactant or a product. It's formed and then consumed in the reaction. So that's really important. It's formed and then consumed. It's not added in. A catalyst would be added in and then come out as a product. This one is formed in the reaction and then is consumed in the reaction. Okay? So now your NOF2 is an intermediate. AP question. Which is, what is your intermediate? What is your catalyst? There is no catalyst in this one, but that is an AP question. What is an intermediate? Like what chemical? And you can see that K1 and K2 are for two different steps. So if you are going to write the rate law for this, your rate is going to be equal to K1, which is the slow step, and you're going to cancel everything to make sure that you are getting everything that you need. So let's see, I have 2NOF, right? Yep. Okay, so that does add up. So NO, the concentration of NO, right, to the X, which I'm not sure because I'd have to see, wouldn't I, right? F2 to the Y. And I don't know what X and Y are because I'd have to see the data, right? Everybody with me? Now I go back and I look and I see, okay, well, that's the rate of the whole equation. That doesn't matter. What I'm looking at is that the rate of the slow step? And it is. Does that equation follow the slow step? Doesn't matter that it's up here. I don't care about that. I care about the slow step. Okay? All right. Let's take a look here. Okay. An example problem. Okay, so if we're looking at this one here, all right, here we go. All right. So here's the mechanism, right? Hang on. So there's the mechanism. And we want to know that it's going to produce the rate law. So we look and we see here's your BR2 and your N2O2, right? And this is your slow step. Now, right. So you look and you see this is an intermediate. So they're going to cancel. So that should give you the ultimate equation, which is 2NO, right? Plus BR2 gives you 2NOBr. And then once you break this down, you can see that your rate law, so this, using the second step as rate determining, this would be your rate law, right? This would be your rate law. But this is an intermediate. So what you're going to do instead is, well, this starts to get really complicated, which I don't want to get into because we don't need to get into it. So that's not what I wanted. Really, I just want to look at the intermediates and the catalysts. That's all I want to look at. So I'm trying to find a catalyst. So here's one. Here's another one. All I want to do is look at the catalyst because you don't have to break down the rate laws at all. So here's a slow step and a fast step, and then the overall. So here's the NO2 and the NO2, right? So we're going to cancel the NO2s, 1, right? NO3, this is an intermediate here. Okay? And when we add these together, we get 1, 2, but 1 cancels. So there's 1 here, that's that. And then the nitrogen monoxide and the carbon dioxide. So what we see is 1 intermediate, and that's what we're looking at. So you're looking at, does the rate law match? I had a problem that I was going to show you. Does the rate law match the slow? And then hang on. Does the rate law match the slow step? What's the catalyst? What's the intermediate? And then there are going to be questions on draw the graph, right? And putting in the catalyst, everything that we did today. So here's one. Here's a good example. 61. One mechanism for the destruction of ozone is this. Which species is a catalyst? So you can see that NO is added here, and then it comes out at the end, which means it's a catalyst. It was added in, and it comes out as a product. So it is a catalyst. Okay, it's unused. All right? Which is an intermediate. So here's NO2, and here's NO2. So NO2 is an intermediate. All right, that's the rule. The rule is if it's put in as a reactant and it comes out as a product, it's a catalyst. Why? Look, it's going to cancel out. It's like it never even showed up. All it did was speed up the reaction. Okay? And the same thing for the intermediate. It was made and then it was gone. All right? Okay. So then if the there we go. If the activation energy is 14 joules for the same reaction, when catalyzed, it's 11.9. What is the ratio of the rate constant? All right, we didn't do that, so we don't have to do that. They don't have to do that. That's basically all they want to know. I'll pull up free response questions tomorrow. You'll have practice analyzing the things tonight. But basically, that's all they're going to want to know is mechanisms. Do you understand? Right. The rest of it is just weirdly goggly. It's only one small section in your chapter. This last section. That's it. This last section. And for the test, all they want to know is, can you identify catalysts, intermediates, and if they give you a rate law, can you match it and make sure that it matches the slow step? So if they tell you this is the rate law, you have to be able to go to the slow step and say, no, this doesn't match. Okay? So take a look at the problems tomorrow. This is the last section in this chapter. So tomorrow we'll review everything. I'll try and print out. It's such a disaster with the printer. And we'll look at Thursday, I guess, for a quiz. All right? I thought I had Sorry, that was not, I had a problem set aside that was going to explain the whole thing, and I just don't know where the problem went.